According to Michio Kaku, black holes are the ultimate testing ground of the divine. In their vicinity, time distorts, space collapses, and the very laws of physics fall apart. Now, Kaku believes he has uncovered the truth about what lies inside a black hole. Long regarded as the most enigmatic entities in the cosmos, black holes are regions where space, time, and matter are crushed to unimaginable extremes. For decades, the mystery of what exists beyond the event horizon has puzzled scientists. But that mystery is finally starting to unravel. With revolutionary theories, unprecedented observations from the James Webb Space Telescope, and bold advancements in quantum gravity, we are now beginning to illuminate the darkness. And what we're discovering is reshaping our understanding of the universe itself. Picture a realm where time ceases to flow, space twists in on itself, and all known physical laws reach their breaking point. These environments are so intense that even the most fearless physicists would rather retreat. Black holes aren't just bizarre objects in space, they are the wildest, most mind-bending phenomena our universe contains. Physicist Michio Kaku refers to these terrifying regions as God's test laboratories, and it's no coincidence. Near these dark giants, the very foundations of physics seem to unravel. Space and time, energy and matter, everything we thought we understood begins to behave in unexpected ways. At first glance, black holes might appear to be nothing more than massive vacuum cleaners in space. But a deeper look reveals they are far more enigmatic, and perhaps even more creative, than we ever imagined. Black holes, the universe's most extreme and secretive architects. Once thought to be mere remnants of collapsed stars or the dense cores of galaxies, black holes are now emerging as cosmic superstars. For years, scientists viewed them as impressive but destructive forces, enigmatic and extreme. But today, our understanding is shifting. Black holes are proving to be far more significant than once believed, taking on an entirely new and profound role in the cosmos. Michio Kaku has authored numerous books and articles exploring black holes and other key areas of modern physics. Years ago, he regarded black holes as enigmatic phenomena whose true importance may have been overlooked. Recent discoveries from the James Webb Space Telescope reinforce his perspective. Scientists have found that both galaxies and black holes existed much earlier in the universe than once believed. Stunning images from this powerful telescope suggest that colossal black holes may have formed even before the first stars and galaxies appeared. This challenges current scientific understanding. Traditionally, black holes are thought to form when massive stars exhaust their fuel and collapse, meaning they come after stars. But if these massive entities came first, their role in shaping the universe could be far more profound. Black holes are regions where the known laws of physics break down. Their gravitational pull is so immense that even light cannot escape. Once an object crosses the event horizon of a black hole, it can no longer escape the intense gravitational pull. This boundary is defined by what's known as the Schwarzschild radius. For a black hole with the mass of our Sun, that radius is about 3 kilometers. But if Earth were compressed into a black hole, its Schwarzschild radius would be just 9 millimeters, shrinking the entire planet into a sphere the size of a peanut. The gravitational force at this boundary is immense. In fact, near the event horizon of a stellar mass black hole, spacetime becomes so warped that a single second could appear to last years to a distant observer. This phenomenon, known as gravitational time dilation, was predicted by Albert Einstein in his general theory of relativity, long before black holes were confirmed to exist. Black holes are remarkably simple in terms of measurable properties. They can be defined entirely by 3 characteristics: mass, angular momentum, or spin, and electric charge. Everything else about the matter that collapsed to form them is lost, a concept known as the no-hair theorem. Most black holes we know of are electrically neutral, yet they can spin at astonishing speeds, close to the speed of light. Their density is also extraordinary. A black hole with the mass of Earth would be even denser than the nucleus of an atom. At their core lies the singularity, where pressure and the curvature of spacetime become infinitely large, according to current mathematics. This is where every existing theory reaches its limit, making black holes the ultimate testing grounds for physics. They might even unlock a deeper understanding of the natural world. The mass of black holes varies widely. Stellar black holes range from about 3 to 20 times the mass of our Sun, while intermediate black holes can weigh anywhere between 100 and 100,000 solar masses. At the extreme end, supermassive black holes found at galactic centers can tip the scale at several billion solar masses. Sagittarius A*, located at the heart of the Milky Way, is relatively small, with a mass of around 4.3 million suns. While these numbers are staggering, the true mystery of black holes might lie in the unseen, minuscule realms. If black holes are, in fact, wormholes or portals to other dimensions, they could also be creators of new realities. According to physicist Michio Kaku, we may not need to look beyond our universe for answers. It's possible that black holes are colossal engines that recycle matter and energy within our own cosmos. Lost forever? Maybe not. The infamous information paradox could hold the clue. This unresolved issue in modern physics centers on a vital question: what happens to information that falls into a black hole? Quantum mechanics asserts that information, the very fabric of matter, can never be entirely destroyed. In theory, if the precise quantum state of a particle is known, its entire history can be reconstructed. However, this principle breaks down when it comes to black holes, if they truly exist only to destroy. When an object crosses a black hole's event horizon, it vanishes from view and becomes inaccessible to any outside observer. Its information appears to be lost. Once the black hole eventually evaporates through a process known as Hawking radiation, first proposed by Stephen Hawking in 1974, the information it contains seemingly vanishes as well. This presents a major conflict in physics. According to general relativity, the information is lost forever behind the horizon. But quantum mechanics insists that information can never be truly destroyed. These two foundational theories give opposing answers. Hawking did show that black holes emit a tiny amount of radiation, apparently purely thermal, but it's still unclear whether this radiation carries any information. It's possible that information escapes from black holes through an unknown mechanism. If that's the case, the implications are profound. Escaping information could be reused, forming the building blocks of the universe once again. Black holes would not just be destructive forces, but also engines of creation. The holographic principle expands on this idea, suggesting that all the information is preserved on the event horizon itself. And if black holes are not ultimate dead ends but instead gateways to other regions of spacetime, the information could travel to alternate dimensions or universes, where it might be recycled and reborn. The holographic model is gaining increasing attention in current research. This theory suggests that all information in the universe is encoded on the surface of an event horizon, much like a hologram, which produces a 3D image from a 2D surface. In this framework, black holes could serve multiple roles, as cosmic garbage disposals, massive recycling systems, and even as projectors shaping the universe we perceive. General theory of relativity, from equation to reality. For a long time, black holes were nothing more than a mathematical concept found in Albert Einstein's notes. Eventually, they emerged as one of the most astonishing theoretical predictions in modern physics. Einstein's general theory of relativity redefined gravity, not as a mysterious force, but as the curvature of spacetime caused by mass and energy. It was German physicist Karl Schwarzschild who first discovered an exact solution to Einstein's field equations. During his calculations, he identified a strange boundary, which would later be known as the Schwarzschild radius. Initially, this boundary simply marked a specific region in space.